Hey everyone, Math 103. We're working on the last lesson in Unit 3. We're jumping ahead to sections 9.2 and 9.3, solving linear inequalities. Let's take a look at the introduction. In a college class, the students need to average at least 93 to earn an A. A student has scores of 89, 98, 91, and 90 on the first four exams. What range of scores on the fifth exam will earn the student an A? So we'll learn how to set up and solve inequalities like this. So like the question in the introduction, there's a lot of questions in math where the answer is a whole range of possible values. So for example, a company may want to know the income needed to be profitable. Well, there's some certain minimum value to that, but also any amount of income above that minimum value is also going to lead to profitability. So the answer is a whole range of incomes. So an interval is a range of numbers on a number line. So here we've got a couple of number lines, and we're going to look at the interval between 3 and 9. Now there's several different ways to indicate a range of numbers. First is with an inequality like this, where x can be any value between 3 and 9. And we can graph this on a number line. When we graph, we have to indicate the endpoints. So we have an endpoint at 3, and I'm going to put a parenthesis there to indicate that the range of answers ends at 3. And it also ends at 9. And then what we're going to do is shade in between them. And there's the graph for the interval between 3 and 9. So I use parentheses because those numbers are not included in the range of values. It's every number between 3 and 9. So 4, 5, 6, 7, and 8. Those are all in the solution. As is every number in between. So like 5.2, 6.13, and so on. But the endpoints 3 and 9 are not included. And we can tell that from the inequality. It's strictly greater than here and strictly less than here. So that means 3 and 9 are not included. But what if we do want to include 3 and 9? Right, then we're going to use different symbols for that situation. If we want to include the endpoints, then we use less than or equal to. So it's going to be greater than or equal to 3 or less than or equal to 9. So to indicate that on the graph, that we're going to include the endpoints, we use square brackets on 3 and 9 instead. So there's the graph for every number between 3 and 9, including 3 and 9. Take a look at your turn number 1. We're going to graph the inequality. Negative 7 is less than or equal to x, which is less than 4. Graph that one on the number line. Now when you make your graphs, you should be putting your graphs right on the number line. For demonstration purposes, I'm going to be drawing them right below it so I don't have to keep drawing the number line over and over again. So we're starting with, on the left, negative 7. And it's negative 7 less than or equal to x. So we're including negative 7 in the set. So I put a square bracket here. And we're going out to 4. Draw a line out to 4. But x is strictly less than 4. So 4 is not included in the solution. So we're going to indicate that with a parenthesis on the right. So that's what the graph looks like for negative 7 less than or equal to x less than 4. Now another way to indicate solution sets is using set builder notation. Now set builder ends up being easier to use than interval notation because all we have to do is take our inequality and stick it in a couple of curly braces with a little bit more stuff in there. So here's what set builder notation looks like. Let's say we want to write negative 8 is less than or equal to x less than 4 in set builder notation. All right, set builder begins with a curly brace. These are a little hard to draw, so if you just make some kind of a curly looking thing, I'll know what you mean. Next, we announce the variable we'll be using. So we're using x, so x goes here. And what follows then is a vertical line. And this is read as such that. So all values of x such that x is between -8 and 4. So you just take your inequality and stick it in there. So this will be the same, and every time you use set builder notation, we'll have curly brace, the variable, a line, and a curly brace on the end. And then you take your inequality and stick it in there. Your turn, number 2. Write x is strictly greater than 12 in set builder notation. So that's what that one looks like. Same notation, curly brace, x, line. There's our inequality. Finish it off with a curly brace. Now, interval notation looks quite a bit like what we're doing on the graph. We're going to be using the exact same symbols. So that's one nice thing about interval notation. Now take a look at the table, and we're going to see several different ways of writing the interval between A and B, depending on whether or not we're including the endpoints. So something like this, A is less than or equal to X, less than or equal to B. Just like over here where we used brackets on the ends, we're going to use brackets now on the ends of interval notation. So you write the two numbers in between separated by a comma. So here are your endpoints. This tells whether or not the endpoints are in the set, and that is interval notation for all numbers between A and B. And if we wanted to do strictly less than, then we, just like with this graph, we're going to use parentheses. So it'd be A comma B. And then on the right-hand side, you can see what it looks like with some real numbers in there. So let's do one with some real numbers. Let's say we do -3 is less than or equal to X less than, oops, not B, 5. Now I've got one that's mixed. We've got less than or equal to, so we're going to have a bracket on the left. Then the first number, -3, goes here. 5 on the right. And this one's just less than, so a parenthesis on the right. So you can have one that has different symbols on the outside. Now, not all intervals are going to have two endpoints. Some of them just go on forever. Like our initial example about whether or not a company can be profitable. Well, any amount of income over a certain minimum amount means the company is going to be profitable. So that number can go as high as we want. So we're going to use infinite intervals for that situation. So let's say we want to represent the inequality x is greater than or equal to 5. So any number 5 or bigger is in the solution set. Now we've got greater than or equal to, and 5 is the lowest number, so 5 goes on the left. When we use interval notation, the smaller number always goes on the left. All right, now comma. Now we need some number over here. But x can be as big as we want. So that means we're going to use this symbol. It looks like kind of like an 8 turned on its side, infinity. Now we've got the interval from 5 to infinity. That means any number greater than 5. Could be 10, could be a million, could be a billion, just goes on forever. Now if we want to do less than, let's say we want to do x is less than 4. It's any number that's smaller than 4. So we're going to go to the left on the number line all the way to infinity. But this time, we're making it smaller. So instead of positive infinity, we go all the way to negative infinity. Because on the number line, we keep going this way, we're in the negative number. So down here, all the way to the left is negative infinity. So the smallest number is negative infinity. And the largest number is 4. But we're not going to include 4 because it's strictly less than, so we have parentheses here as well. Now notice that on this one, even though we have greater than or equal to, we got a square bracket here, but I'm still using a parenthesis on the right-hand side. And the reason is, if I were to use a bracket here, that would mean that this number is part of the solution set. But infinity isn't an actual number. It's just kind of an idea. The idea is that it goes on forever. So since it's not an actual number, we can't include it in the set. So since it's not in the set, we use a parenthesis. All right, your turn, number 3. Graph each inequality and write it using interval notation. First one, x is less than negative 2. So it's strictly less than, so negative 2 will not be in the solution set. It's less than. There's no boundary over on the left-hand side, so that means we're going all the way out to negative infinity. So we'll start with negative infinity. Remember, smallest number is on the left, comma. Negative 2 is our other boundary, and it's strictly less than, so it's a parenthesis there. Now on the graph, we're going to start with negative 2, going all the way to the left. So put a parenthesis there, move all the way to the left, and then when we get down here, just color in an arrow, and the colored in arrow means we're going infinitely to the left. Next up, we've got all numbers between negative 3 and 1, including the endpoints because it's less than or equal to. So in interval notation, we'll start with a smaller number on the left, go to 1 on the right, and brackets indicate that negative 3 and negative 1 and positive 1 are in the solution set. So the graph for this one, we'll start at negative 3. Bracket there should match interval notation, so bracket and bracket. Another bracket at 1, and then shade in between. Next up, x greater than or equal to 9. So that means 9 is the smallest number in the set, and we're going infinitely to the right. It is greater than or equal to, so we'll start with a bracket, smallest number on the left, going all the way out to infinity on the right. Since it's infinity, that's a parenthesis. The graph for this one, we're going to start at 9 with a bracket to match the bracket here, all the way to the right, and then shade in the arrowhead to indicate we're going off to infinity. Next up, now we've got a mixed one. We got less than or equal to and less than. So for less than or equal to, use a bracket. 4 is the smaller number, that goes on the left, going all the way out to 8 on the right, strictly less than, so that is a parenthesis there. And just a reminder, make sure you're drawing your graphs right on the graph. I'm just putting mine below it so I don't have to keep erasing this. All right, matching 4 on the left, we have a bracket here, going all the way out to 8 on the right, and a parenthesis there. So there's the graph for 4 less than or equal to x less than 8. So this is how we're going to represent the solutions to the inequalities that we're going to solve. All right, next up, we're going to be solving linear inequalities. And we're going to solve these almost exactly the way that we solve equations. But there are some important differences. So the first difference is what happens when we use the multiplication property with negative numbers. So when solving an inequality, we can multiply both sides of the inequality by some negative number c, but when we do so, we have to flip the direction of the inequality. Let's see why that's the case. So here we have an inequality. This is clearly a true statement. Negative 2 is less than 7. Now I'm going to use the multiplication property. If I multiply by a positive number, so I multiply both sides by 2, then we get negative 4 is less than 14. It's still true. Now let's try it with a negative number. I'm going to multiply both sides by negative 2. So negative 2 times negative 2 gives us positive 4, less than 7 times negative 2 is negative 14. Is that statement true? Is 4 really less than negative 14? No, clearly it's not. But if we use multiplication property, where we multiply by a negative number and you switch the sign, that makes it true. 4 is indeed greater than negative 14. That's why we have to switch the direction of the inequality if we ever multiply or divide by a negative number. Here's an example with an actual inequality with a variable in it. So negative 8x is less than 56. So the coefficient on the x is negative. So if we want to solve for x, we have to divide by that negative number. Right? Negative 8's cancel here. So we get x, and we'll switch the direction of the inequality to greater than. 56 divided by negative 8 is negative 7. So our solution is x is greater than negative 7. Your turn, number 4. Solve the inequalities, graph the solution set, and write the answer in interval notation. First one, negative 3x is greater than or equal to 12. So I'm going to divide by a negative number. So now I have to switch the direction of the inequality, so that's going to be less than or equal to. If it's less than or equal to, it becomes greater than or equal to. If it's strictly less than, and we have to switch that one, it becomes strictly greater than. 12 divided by negative 3 is negative 4. So our solution is x is less than or equal to negative 4. So negative 4 is the largest number, and it's less than or equal to, so we're going to use a square bracket on that side. And the solution set goes all the way out to negative infinity. So we got negative infinity to negative 4. And graphing that one, using the same symbol here, bracket, all the way to the left, and it's infinite, so shade in the arrow. Next up, 5x plus 2, strictly greater than 12. So we're going to solve this exact same way we would an equation. Just pretend that's an equal sign. All right, subtracting those out gives us 5x greater than 10. Now we're dividing by a positive number. So we do not switch the direction of the inequality when multiplying or dividing by positive numbers. So this will remain greater than x greater than 2. Now, we have strictly greater than, and 2 is the smallest number, so we'll start with a 2 on the left, comma, going all the way out to infinity on the right, and another parenthesis there. So on the graph, the solution is going to look like, using the same symbol, parenthesis at 2, all the way out to the right, fill in the arrow to indicate it goes on infinitely. All right, part C, we're going to look at a little more complex one here. We're still going to use all the techniques we learned for solving equations. So when solving equations or inequalities like this, first thing we want to do is simplify each side. We don't have any parentheses, so we'll just combine like terms. 6x plus x is 7x, so that gives us 7x plus 3 on the left, so greater than or equal to. Here we've got a couple of constants we combine, 2 and 4, so that's 4x plus 6. Subtracting 4x from both sides. Now these are negative, but subtracting does not mean we have to switch the direction of the inequalities. That's only with multiplication or division. So we get 3x here. And since I got all the x's to the left-hand side, I'm going to subtract 3 from both sides to get all the numbers to the right. So 3x greater than or equal to 3 divided by 3 on both sides. Dividing by a positive number, so we do not switch the direction. X is greater than or equal to 1. All right, interval form. We've got greater than or equal to, so we use a square bracket for the left-hand number. We're going infinitely to the right. So we got infinity and a parenthesis there. So this one, graph is going to look very similar, except we're going out to 1. And since we have a bracket here, we're going to have a bracket on the graph. Part D. So we're going to start this one off by clearing the parentheses through distribution. So distributing the 5 into here, we got 5x plus 15 minus 6x is less than or equal to, and we'll distribute here, 6x plus 3 minus 4x. Now we can simplify each side. 5x minus 6x is negative x, so we get 15 minus x on the left, and on the right, 6x minus 4x is 2x, so 2x plus 3. Now here's where I really like to keep the x term positive, because that avoids having to divide by a negative number and then remembering to switch the sign. That's where I see a lot of mistakes. So I'm going to add x to both sides to keep the x term positive. That moves all the x's to the right, so we're going to move all the numbers to the left. So minus 3 here, minus 3. So that gives us 12 less than or equal to 3x. Now we can divide by a positive number since we kept the x term positive. We have 4 less than or equal to x. So x is greater than or equal to 4. We can always switch this whole thing around if it's easier to read that way. So an equivalent statement to this is x is greater than or equal to 4. Now in interval form, we're going to start with 4, then go all the way out to the right. So 4 comma infinity. And since it's greater than or equal to, we use a bracket there. So that's going to change this graph to start at 4. And we got a bracket here, so I'll have a bracket here. But what if we want an infinite solution? What if we want boundaries on both sides? Like the first example, where we had intervals between 3 and 9. Well, those inequalities are going to look a little bit different. And instead of 2 parts of them, there's going to be 3 parts. Now we're going to solve and graph negative 2 less than 3x plus 7 less than 1. So when we're solving these, the goal is to get x by itself. X is going to be in the middle part here, And then we're going to end up with some number out here and some number out here. These will be the boundaries for the solution set. So let's see what those boundaries are. We're going to solve this just like we do the others, except whenever we do an operation to the middle part, we have to do it to the outer parts as well. So every operation is done 3 times instead of 2 for an equation. Minus 7 here, minus 7 here, minus 7 here. All right, 1 minus 7 is negative 6. Bring down the inequality symbol. We have 3x in the middle. And negative 2 minus 7 is negative 9. All right, now we want to get the x by itself, so we need to get rid of its coefficient. So we're going to divide all 3 parts by 3. So negative 9 divided by 3 is negative 3. We're dividing by a positive number, so these keep pointing in the same direction. So our solution set is all numbers between negative 3 and negative 2. Now these are both strictly less than. So use a parenthesis, negative 3, negative 2, parenthesis. And make sure the number on the left is smaller than the number on the right. So now we can graph this using the same symbols, parentheses, negative 3 to negative 2, and then just shade in between. Your turn, number 5. All right, so we'll start by getting rid of the negative 4. Add 4 to all 3 sides. We got 9 on the left, less than 3x, less than 15. Divide by 3 on all 3 sides. We get 3 less than x less than 5. So all numbers between 3 and 5, not including the endpoints, because we have strictly less than. So in interval notation, we have 3 to 5, like that. And on the graph, same symbols, parenthesis, between 3 and 5. All right, now we're going to look at the application from the introduction. So in a college class, students need to average at least 90 to earn an A. Student has scores of 82, 88, and 94 on the first 3 exams in the class. What range of scores on the 4th exam will earn the student an A? So what we're talking about here is an average. And to find the average of 4 exam scores, we add them up and divide by 4. So let's write out the first 3 exam scores. 82, 88, 94. Then we use S for score for the last one. All right, we don't know that. That's what we're looking for, so that's our variable. Now to find the average, we add them up and divide by 4. So this will be the average score, or this will be the average of the 4 exams for that student. And we need that average to be at least a 90. At least means 90 or above. So this whole thing here, this average has to be greater than or equal to 90. So there's the equation we can solve, or the inequality we can solve, to find the minimum score on that exam. So let's start by getting rid of that denominator. So we're going to multiply both sides by 4. All right, 4 on top, 4 on the bottom, those cancel, leaving just the numerator. So we have 82 plus 88 plus 94 plus s is greater than or equal to 90 times 4, which is 360. All right, now we can add up these values. We add those up, we get 264. So 264 plus s is greater than or equal to 360. All right, now I'm going to subtract 264 from both sides. And we get s is greater than or equal to 96. So the students must score at least a 96 to earn an A. Your turn, number 6. On this one, the student has scores of 89, 98, 90, and 91, and we don't know the last score, so I'll put an S there. And since we're adding up 5 exams for this one, we'll divide by 5. Student needs to average at least a 93, so 93 or greater. So this average has to be greater than or equal to 93. Now to solve this, multiply both sides by 5 to get rid of that 5 there. So 5's cancel, we're left with just the numerator. And 93 times 5 gives us 465 on the right. Now we can add those 4 scores together. And we get 368. So it's 368 plus s is greater than or equal to 465. Subtract 368 from each side. So s is greater than or equal to 97. So that student must score at least a 97 to earn an A. That's it for this lesson. That wraps up Unit 3.